The University of Oklahoma Sooner Rover team is proud to present our rover, Gusteau, for the 2026 University Rover Challenge.
The rover integrates mechanical, electrical, autonomous, and science subsystems into a single platform. Each subsystem is independently tested and validated before full system integration to ensure reliability and functional isolation. The architecture is built around a CAN bus network connecting all subsystem microcontrollers to a centralized compute unit. Communications with the base station are handled via a long-range 2.4 GHz wireless link with a mast-mounted directional antenna supporting telemetry, multi-camera video feeds, and operator control.
To navigate uneven terrain characteristic of mission sites, our rover utilizes a six-wheel double bogie chassis to maintain ground contact and minimize pitch and roll during traversal. This year, the rover incorporates slanted Grouser TPU treads mounted to metal bump stops to minimize tread deflection and preserve the wheel structure. High torque motors paired with planetary gearboxes provide sufficient power to climb inclines, cross obstacles, and operate on soft soil, capabilities that are field tested over dirt hills, trenches, rocks, and confined maneuvering courses. The chassis and wheel design are optimized for strength, stability, and center of gravity management. These tests confirmed mobility performance, motor reliability, and structural integrity under representative mission conditions. During this demonstration, the rover navigates a cone course similar to that seen during the Extreme Delivery mission, maintaining stability and precise control. The PVC payload carried here illustrates the integrity of the mobility and manipulation systems and the overall vehicle's ability to balance held items.
The 5-degree of freedom robotic arm provides precise positioning for manipulation tasks. The arm is controlled via controller, with multiple camera views providing real-time feedback for accuracy and situational awareness during the mission. To reduce weight and improve efficiency, most of the redesigned arm is constructed from carbon fiber. Additionally, a small linear actuator has been added to control the wrist, enhancing its dexterity and reliability for fine manipulation tasks. The arm's modular end effector enables interaction with multiple mission payloads. In testing, it inserts a test tube into a slotted holder, lifts and transports a toolbox, and performs operations with the mock lander, demonstrating its versatility. On the mock lander, the arm was able to successfully type SOBRO, open a latch door, insert a USB, and operate a switch. The arm can also pick up small objects such as a screwdriver from the ground, showing its capability for fine manipulation under mission conditions. These coordinated actions validate the accuracy of, reliability, and repeatable performance of the ARM subsystem. Overall, the design prioritizes weight reduction, operational efficiency, and consistent performance across all fine manipulation tasks.
The science package includes a collection system and a testing system. The collection system is a linear actuator that drives an auger into the ground. A chute near the rear of this apparatus evacuates the collected material, allowing it to drop down and in front of the testing system mounted beneath the rover body. Once the auger reaches depth, the testing system opens the collection ramp to allow samples into the rover. Within the testing system, 3 containers are mounted in a rotating carousel, allowing operators to collect samples selectively. The samples are monitored using live feed video and can be remotely sealed for subsequent manual retrieval. 2 of the 3 samples are then tested for biological evidence using the Benedict's test and the 9-hydrogen test, respectively. These colorimetric tests allow operators to identify test results using the remote video feeds during the challenge, while offering a high degree of experimental confidence.
For autonomous, the team is continuing from last year's rewrite. The team replaced its depth camera with a LiDAR device. It allows stable real-time processing and reliable path planning over Nav2. We don't use or require a GPU for processing the LiDAR's point cloud data, which greatly improves power efficiency. For path planning, we incorporate LiDAR, our new GPS, and an IMU through sensor fusion, allowing autonomous navigation of difficult terrain and allowing us to use obstacle avoidance. Our new global shutter camera reduces motion blur, artifacting, and shaking. It helps us reach consistent real-time Aruka detection via OpenCV. We're now using YOLO 26, a leading object recognition and pose estimation model. We can estimate an object's distance from the rover and create a waypoint, sending it to our navigation stack for normal coordinate navigation.
The Sooner Rover team presents a fully integrated rover capable of mobility, manipulation, science, and autonomous tasks. Systematic design, modular integration, and rigorous testing ensure mission readiness in extreme environments. We thank our sponsors, faculty advisor, and supporting organizations for enabling this project, and we look forward to demonstrating the rover at this year's University Rover Challenge.